Hello everyone, I am Dr. Fawzul Atiq giving some series of lecture for the course Discrete Mathematics. So in the previous lecture, we have seen that what is compound proposition, then few examples of compound proposition, right? Then at the end, we have learned that when two compound propositions are equivalent, right? That means whenever they have the same truth value, you called it as the two compound propositions are equivalent. So we'll continue similar kind of thing, right? So let us see. So two terminology we learned for this one, that a compound proposition that is always true, no matter what are the truth values of the propositional variable that occur in it, is called a tautology, right? So tautology is like it's a compound proposition. Now we have seen that a compound proposition have mm, truth value is either true or false depending on the truth value of P and Q, right? But tautology is such a compound proposition where you will always have truth. Truth value is true, no matter what are the truth values of P and Q. And we can create also such kind of thing. We'll give you some very good example also. So like first example, the simplest example is, so I'll give you something. Suppose I have a proposition P, then negation of P, and then P and negation P. Look at that. What is the truth value of this? Sorry, I should make it as PP and then or PI. I made it a mistake. Yeah, so I talked about P or Q, not P. Now, what are the all possible cases? P can be true, P can be false. Now, depending on P values, not P will be false, and this will be true. Then P or not P. What are the truth values of this one? Because one of them is true, therefore this is true. Next one also one of them is true, therefore this is true. Now see, no matter what is the truth value of P, that P and not P is always true, right? So therefore, this one P and not P is a tautology. P and not P is a tautology, right? So you called it as a tautology. Now, I hope you got the idea for the contradiction example. A compound proposition that is always false is called a contradiction, no matter what are the truth values of the propositional variable occur in it. Now, I hope all of you can guess that. So if P or not P, I have the tautology. Therefore, definitely P and not P will have always truth value is false. Therefore, it's a contradiction. Why? Like P and not P. So the first one that should be false. Next one is also false. Therefore, P and not P is a contradiction, right? So these are the simplest example of tautology and contradiction. So it is called a contradiction. Easy? Okay. So whatever I discussed, it is written here. Now the definition of contingency. Now a compound proposition that is neither a tautology nor a contradiction is called a contingency. Now most of our compound proposition is like that, right? So if it is some truth for some truth values of P and Q, if I have it is true and some truth values of the propositional variable it is false. If I have both the case, then we will consider it as a contingency. And our general compound propositions are like that. So tautology and contradictions are special cases. Okay. Now, the compound proposition P and Q are called logically equivalent if P if and only if Q is a tautology. Then the notation P equivalent to Q, we denote it by that P and Q are equivalent. So this is the notation. Now we discussed this part in the earlier class as well. We said that P and Q are equivalent if they have the same truth value. Now the same definition we are saying in terms of tautology. What we are saying, two propositions are compound propositions are equivalent or logically equivalent if P if and only if Q is a tautology. Now P if and only if Q means what? It is when it is true, whenever both P and Q have the same truth value. Therefore, P and Q have the same truth value, then only it is always true. Therefore, P and Q are equivalent. Right? We'll understand this through some example as well. So look at this example. Show that not of P or Q and not P and not Q are logically equivalent. Now, how do you prove that? So you can use the truth table, right? So what to do? What I required? I required P, I required Q, I required not P, I required not Q, then I required P or Q, then I required not of P or Q, and finally I required not P and not Q. Then you have to consider all possible cases. So do the truth table. Four different cases will have four different combinations. So both P and Q are true. P is true, Q is false. Then Q is false, P is false, Q is true, and both of them are false. Then what is not P? Not P is this one. If P is this one, not P is false. This is false, then true and true. What is not Q? Not Q will be false, true, false, and true. P or Q. P or Q is what? P or Q will be, you know, that basic formula. So I said in the previous classes as well that please do practice the small truth table. That will be useful to create this kind of logical equivalence statement. Right. So if you know what is the OR operator truth table, what is the negation truth table, what is the implication truth table, you can do these things easily. Okay. So P or Q, we know that it is true always except the case when both of them are false. So it is true, 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 and this is false. The negation of P or Q. So now this is exactly opposite of it. So F, 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 and T. Now not P and not Q. Not P and not Q, right? I have to take this two. Not P and not Q. So the first one, both of them are false, so false. One of them is false, this is also false. Next one of them is false, this is also false. But the last one is true. Got it? So now see that a this quantity and this quantity, both of them have the same truth value, right? So therefore they are equivalent according to our previous day definition. But today we have learned that if I have two compound proposition, maybe A and B, and then they are equivalent if the biconditional statement is a tautology. Now see what could be the biconditional statement. A if and only B. Now we know that biconditional statement is true whenever both A and B have the same truth value. But look at that, they have the same truth value. So this is true, this is true, this is true, and this is true. And therefore I have A if and only B is a tautology. And what does it mean? Therefore A and B are equivalent. Right. Therefore, these two are equivalent. So to prove two compound propositions are equivalent, you may do up to this step, done, or you may, if you want to apply the tautology definition, you can do this one also. So if you see both the columns have the same truth value, you can immediately declare that they are equivalent, or you can extend one more column that you show that A equivalent to B is a tautology. Right? Always there too. I hope it is clear. So now there is, you observe something that what we have proved that we proved that negation of P or Q is equivalent to not P and not Q. So we inside we had OR operator, then whenever we have negate it, we got it as AND operator. Right? Individually they become not of P and not of Q. Right. So these things you have seen it in your set theory also. In your plus two level, you must have seen this kind of thing. In where you have seen, try to recall. Yes, you have seen in set theory. In which way? You know, right, that A union B whole bar is equal to A bar intersection B bar. Remember? So it is like that. Similar kind of thing. So initially you had union, now it become intersection. So this kind of pattern here also it is following. So you have it is negation or become and individually they become negation, right? So what was that law? It was the De Morgan's law for set. Now this will be De Morgan's law for proposition, right? So if this is one part of the De Morgan's law, can you guess the other one is what? The other one should be that negation of P and Q will be equivalent to, now again, this and will become or, so negation P or negation Q. So this is the another part of the De Morgan's law, right? So immediately after that, okay, this is the of the previous one. Now look at that, so that not of P and Q and not P or not Q are logically equivalent. So this is the second part of De Morgan's law. You can easily prove it with the same way, the way we have done it the previous one. Just, but you should do it. All of you should practice it. Do the truth table and show that both of them have the same truth value. Then finally, we got the De Morgan's law, right? So not of P or Q is equivalent to not P and not Q. Not of P and Q will be not P or not Q. So this and or are getting exchanged. Now onwards, whenever you understand that, okay, these are De Morgan's law, you can use them as a formula, right? So this is the beauty of formula. So now you have proved it. Now you have to remember it also. So now onwards, you use them as a formula. Now we have another logical equivalent statement. This is very, very important one. But first you prove that these two are logically equivalent. So what you have to do? Again, using truth table, P, Q, I require P, Q, I require not P, then I require P imply Q, then not P or Q. So just quickly finish the truth table. Quickly we can finish it. So T, 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 F, F, T, and F, F. So these are four possible cases. So not P is what? False, false, true, and true. P imply Q is what? But we all know that P imply Q is false whenever P is true, Q is false. So this is the only case where I'll have false. All other cases it will be true. And then not P or Q. Not P is there and Q. So you will take or between these two, right? Not P or Q. What will happen? This is true. This is both of them are false, so false. This is also true and this is also true. Now what we have observed that both the P imply Q and not P or Q both are logically equivalent because they have the same truth value. If you can use the tautology definition also. So if you say that it is A and this is B, then we can say that A if and only B is always true. Therefore, A if and only B is a tautology and A and B are equivalent, right? Therefore, A is equivalent to B. Therefore, this is equivalent to this one. Now, this one is a very, very important logical equivalence statement. We may use it in several places. So please do remember that. Consider this as a formula. P imply Q is equivalent to not P or Q, right? Consider this as a formula. Okay. Now, as I mentioned, this one is very, very important one. P imply Q is equivalent to not P or Q. Consider this as a formula. Now look at this one. Show that these two are logically equivalent. So how can you prove it? Again, this one also you have to prove it using truth table, but one big difference is there. So initially you have seen that for the negation operator, if P was only one variable, then negation P has the same variable, right? So one distinct variable was P. So in the truth table, we had only two cases, true and false. Whenever we move to the little complicated one, P and Q, P or Q kind of thing, so two variable was there. And we have seen that in the truth table, we had four possible cases, TT, TF, FT, and FF. Right, so four different possible cases we have seen. Now, these things, uh, you should get an idea that if you have two variable, then the number of possible cases is 2 square. If you have one variable, 2 power 1. Now in this one, look at this. How many variables involved? Three variables involved, right? P, Q, and R. So there are three variables. So how many possible cases you will have? 2 to the power 3 means 8 possible cases. So 8 rows will be there in the truth table, right? Okay, now let us do it. So we will have a big truth table, which will be big, maybe big, but very easy. If you know the basic truth table, you can do this in very easily, right? So what I required three variable P, Q, R. Then individually I required uh, Q or R. Then I required P and Q. I required P and R. Then I required the big one, P and Q, R, P and R. And I also required the first one I forgot. Or maybe what I will do, I'll keep it there. I need one more, so I required that P and Q or R. So these things are required. Now the truth table will be a little bigger, so I'm making a big one. We'll see how much big it required. this one. So you have to consider all possible cases of truth value, right? So P, so all of them can be true. Two of them can be true, one of them may be false. Two of them may be false, one can be true, and all can be false, right? So all possible cases you have to consider. So I'll first write down the all possible cases. So here it will be true, true, true. All of them are true. Then two of them true, one is false. So true, true, false, true, false, true, false, true, true. Next, we'll consider the cases where two of them are false, one is true. So false, false, true, false, true, false, and true, false, false. And finally, we have the case where all of them are false. So false, false, false. So we have considered all possible combinations, right? So there are 8 such cases. And as I mentioned, if you have 3 variable, you have 8 possible cases. That's what is happening. So we have considered all possible cases. Now we'll slowly do the finish the truth table. These are AND operator, OR operator only. So if you know the basics, you can be easily do it. So Q or R. So what will happen? This will be true, 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 false, and false. Then P and Q. P and Q is first two and operator. So this is true, then false, 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 finally also false. P and R. P and Q we have done P and R. This is true, then false, then true, false, 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 and false. So I made a mistake. P and Q, this will be true actually. The second part. This will be true. P and Q we take now. Okay. Now P and Q are R. P and Q are R. So this row, and this column and this column. P and Q are R. So what will happen? So T, T, T. Now this is the AND operator, right? P and Q are R. So all three are T. Then false, 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 and false. And finally, P and Q or P and R. So this one, and this one. Correct? And OR operator they are. So true, then also true, then also true. But all of them are false. So false, 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 and false. Now see that last two columns, I can see that they have the same truth value always. Right? Therefore, what you can say? We can say that this one and this one are equivalent because they have the same truth value. Got it? Now again, this kind of thing you have seen it in somewhere else, right? This kind of thing you have seen it somewhere else also. Like what I mean that, so you have proved that P and Q or R is equivalent to P and Q or P and R. So this P is getting distributed. It is kind of distributive law of sets, correct? So this is the distributive, one of the part of distributive law of proposition. I hope it is clear. You have seen this kind of formula in set theory that P union, like A union B intersection C is equal to A union B intersection A union C, like this kind of formula, this distributive law for sets. So this is the distributive law for proposition, correct? So if that is the case, you must have guessed that what will be the next other one, other distributive law. You should have two distributive law. So this will be exchange, right? P and Q are R. So it will be now P or Q and R. And then accordingly it will happen. Yeah, so this is what I was talking about. You can easily prove this. So do this one at your home, do practice it and see that they are equivalent, right? So both of them together, we call them as distributive law. Both of them together, we call them as distributive law. P and Q or R is equivalent to P and Q or P and R. So this and or, so this P is getting distributed over the inside portion, Q or R. I hope it is clear. So please do practice for them, each of the proof. Now, in this way, the way we have proved that, in this way, we can prove several equivalence statement, several compound propositions which are equivalent, right? So here we have listed down all of them, which is required. You consider them as formula. So all of them are very easy to prove. You please verify some of cases. If you have doubt, you please verify the way we have verified previously. Just using the truth table, you can do it, right? So here, most of the things you already know. De Morgan's law, you have already done. Distributive law, you have already done. Then negation law, you have already done. And other things are double negation law, you have already done. These are easy, right? And these things, that identity law, domination law, independent law, these are also very easy to prove. If you have P and T, it will be equivalent to P. If you have P and T, it is equivalent to P. You can see, just check it the down truth table. You can see that yes, they are equivalent. P or P, it is equivalent to P. P and P equivalent to P. These are easy. P or T equivalent to T. P and F equivalent to F, always. And then commutative laws, associative law will also happen. Commutative law is just nothing but that P or Q equivalent to P, Q or P. And then associative law is P or Q or R, and then you do the second part. So these are associative property, right? Easy. So these things for this portion, like for the equivalence case, it will be easily. You can remember, you can also understand, you can also verify. Then we have another one called absorption law. That is P or P and Q is equivalent to P. This Q is getting absorbed, so you call it as absorption law. Similarly, P and P or Q is equivalent to P. Again, Q is getting absorbed, so you call them as absorption law. So all these things you please verify. Mostly you will be using De Morgan's law, distributive law, right? And then the negation law and identity law, this kind of thing mostly will be using in several places. But please do remember them. Just practice them, you will understand. Now I will discuss this one. Now see, look at this problem. So that the first one, not of P imply Q and not P and not Q are logically equivalent. Now, till now, what we have learned, that we have proved it two compound propositions are equivalent. If like just you have proved it using truth table, right? Now you know a lot of formula. Why you will always prove them using truth table? Why can't we apply the formula? We can apply the formula and I'm going to do it, right? So now onwards, wherever possible, we'll use the formula, because you know that De Morgan's law, distributive law, negation law, all these are formula. You know it already. You have already proved it. So we'll use them as a formula. Okay. So we'll prove this one. So what you have to show, negation of P imply Q. This is equivalent to. Now I already said that there is a very, very important one that you consider is a formula. It is an implication law. One can say this P imply Q is equivalent to something. What was that? So today's class only we discussed. So P imply Q is equivalent to not P or Q, right? So let us apply that one. So negation P, it is as it is. I had it. Then P imply Q. This portion is equivalent to not P or Q. Not P or Q. So by implications law. Then after that, it is very easy. Negation of something or something. Negation of something or something. We know the De Morgan's law. We can apply De Morgan's law. So it will be negation of negation P. That will become P. Then add or will become and negation of Q. Done. See, within one line you have finished this proof. If you apply the formula, you don't have to do the truth table. Just apply the formula, you will do it. Right? So this is what we need to show, that not of P imply Q is equivalent to P and not Q. We are done. I hope it is all of you understood. So this is the formally it is written that because we have P imply Q is equivalent to not P or Q. So this is equivalent to this. And they can apply De Morgan's law, and by double negation law we can do that. Okay. Now we have another example. Show that this and this are logically equivalent. Show that this one and this one are logically equivalent. Again, we can do, and here it is mentioned that you cannot apply the truth table. You have to prove it by developing a series of logical equivalence. What to do? So let us try. You can easily do. You may also pause the video and try by yourself. Apply the formulas and do it. See, until you do, you will not learn. If you just listen the lectures and listen the class, you will half learn. But whenever you practice, whenever you do it by your own, then only you will learn 100%. Right? You may pause the video and do it by your own, and then you may come back and see the video. Okay, let me do it. So not of P or not P and Q. We have to prove that this is equivalent to not of P and not of Q. How to do it? So we can apply the, see, I have two propositions which are separated by OR operator. So we can apply the De Morgan's law outside, or inside we have this P or P and Q. So the inside portion we can apply the distributive law, right? So we can do both and we'll come up with the final answer. So what I will do, inside portion first I will do. So I'll keep negation it as it is in the outside. Then inside portion I'll apply the distributive law. So what will happen? So P or not P and P or Q. I'll have this one, right? How I did it? By distributive law. So next is, now I have negation and P or not P. What is the truth value of it? We know it is a tautology, right? P or not P, it is always true. So I'll write it as T and P or Q. Done. Because P or not P is always true. Therefore, it is T. Now, if you look at the formula, negation of like inside is true and some proposition, T and some proposition. This will be always equivalent to that particular proposition itself, P or Q. How? I'll show you. T and some proposition is always equivalent to that some proposition. I'll show you the formula again. See, P and some proposition, P and T, like T and some proposition is equivalent to P, right? Identity law. We have applied the identity law there. So therefore, this T and P or Q is actually equivalent to that P or Q. And after that, it is very easy. Just directly apply the De Morgan's law. This will become P and not Q. Sorry, not P and not Q. That is what we want to prove. This is equivalent to that. So our proof is done. Clear? Easy? So all these things, whatever I said, it is very formal, it is written. The first part is distributive law we have applied inside portion, and we get this one. And then we apply the, directly we apply the De Morgan's law here. So this will become that and will become odd and negation. Not of P, so this will become false. This is like, you may change, as I mentioned, right? Sometimes you may apply distributive law in the first and then you may apply De Morgan's law. This is another way of doing the same thing, right? And then not of T will become false. False or something is actually equivalent to that something. And then you apply the De Morgan's law, you have done. See, by applying the formula, we can easily prove this kind of thing, right? So here in the question, it was mentioned that by developing a series of logical equivalents. So you cannot apply it table, you have to use the formulas. Now look at this example. We are about to finish this lecture. So that P and Q is equivalent to P or imply P and Q imply P or Q is a tautology. Now what do you mean by tautology? A compound proposition is said to be tautology if it is always true, no matter what is the truth values of the individual proposition, right? So how we can do, we can easily show it by truth table, but I will insist you not to do it truth table but by applying the formulas. Using truth table, I know all of you can do. You try using the logical equivalence formula. You may just pause the video, try by your own, and come back to continue. By the time, let me do this. So I have to show that P and Q is imply P or Q is a tautology. So I have to prove this is equivalent to T, means true. So what to do? P and Q imply P or Q. Now this kind of thing I cannot apply any formula without applying the implications formula, right? We all know that P imply Q is equivalent to not P or Q. I said several times, this is very important one. You can apply it in several places. Now apply this formula here. So what will happen? Not of P and Q and then or P or Q. right? How, which formula? Because this implications formula. And after that, there you apply the De Morgan's law. So this will become not of P or not of Q. And I had or operator and P or Q. This was already there by De Morgan's law. So I applied De Morgan's law here. Now see, all the operators are odd operator only. All of them are odd operator. So we can apply the commutative law and associative law, right? So we can change them here and there. So just rearrange all of them together. So P or not P. So commutative law and associative law, and then Q or not Q. But we all know that P or not P is what? It is always true. Or operator Q or not Q is what? It is always true. But true or true, it is what? The truth value is true always. Therefore, what you got? This is equivalent to T always. What does it mean? This is always true, no matter what is the truth value of P and Q. Therefore, it is a tautology. So, with the help of logical equivalence proof, we have proved that this is a tautology. Easy? And you could have done it using truth table also. That also I know that you can do it easily, but you should do it both the method wherever required. You should practice by applying formula kind of thing. Right. So here both the proof is written that using the truth table, this one, using the formula, this one. We are done. So we will let me finish the class. I hope you enjoyed. I hope these videos are helpful. If this video you think it is helpful, please do feedback. If you want it in some different way, that also you can write it in the comment box. Right? Thank you very much. We'll come back with the new video in the next class. Thank you. Bye-bye.